Hello, my name is Haeryung Jang, and today I will talk about the paper with the learning data dependency with communication cost. This is the work that when I was in KAIST with the Hyung Song and Professor Yungi in KAIST. So in multi-agent networks, we can observe a collection of data samples generated by multiple agents. This kinds of network data has some uncertainty which has some statistical dependency. For example, in the sensor network, we can observe some sensing data, which is kind of temperature or some alarms or locations, and the sensing data generated from multiple agents can be statistically dependent. And for example, in social network, the opinion status of each individual, which can be characterized by 1 or 0, can also have some statistical dependency. In machine learning area, there are 3 fundamental questions about this reasoning under uncertain data. The first question is how to model this uncertainty of the data, which means that what is the joint distribution from the multiple random variables. So for example, we can choose some class of the Gaussian distribution for the simple example, or we can model the joint distribution of the multiple agents as some more complicated like a Bayesian network. The second issue is about the learning, that is which model is the best and right for my given data. For example, maximum likelihood estimation is to find the best Gaussian model, which is a parameter of the mean or covariance, which is best fitted to my given data. The third one is an inference, which is to answer some meaningful questions about the system according to my given data or model. The most famous examples, the task in this inference is some calculation of the marginal distributions of some subset of nodes, or compute the maximum a posteriori, which is to find the maximum the configuration which has the maximum probability. And the graphical model is well known, the framework which can handle these 3 questions, which represent the multivariate statistics as a structured graph. Okay, so let me first give some simple example of the inference task. For in the sensor network, in the sensors, that they have some sensing data, for example, some alarm, then the sensing data from this multiple targets. And this data have some statistical correlations due to the overlapped correlations of the targets. And the simple example of the inference is known as the data association problem, which is to find the best mapping between the measurements of each sensor to the targets. And for this, inference testing and various applications need, especially in large-scale networks, a need of the scalable, efficient, and distributed inference method has been widely addressed. This method includes the popular the belief propagation or mass product or settling, most of which requires some non-negligible amount of message passings between the agents for distributed operation. However, in many real multi-agent networks, these agents are specially separated so that they can communicate via the physical connections, like this graph. And in most cases, these 2 structures may not be the same. And this fact, from that fact, we face some challenging and important issues in following slides. So some important issues from the fact that these two structures cannot be the same is that first is that there exists a trade-off between the inference quality and the communication cost. And second one is so the trade-off between the inference quality and communication cost is one of the important issues because distributed inference algorithms requires to exchange the information between the agents in the statistical dependency structure, but such an information exchange can be done by given the physical connections. And the second one, in most cases, the statistical dependency between the agents is unknown, which means that we can only have some observed data and we should find the structure between the agents, which is known as the structural learning problem. So here in this paper, our goal is to study the problem of the learning, the structure of the data graph in consideration of the communication cost from the given finite number of data samples. So we have the finite number of samples generated from the known statistical dependence graph, and using that finite number of samples, we want to find the structure of the cost-efficient data graph. So we address the 3 points here. First is what is the cost-efficient data graph, which captures the trade-off between the communication costs from the inference and the inference quality. The second one is how to propose the learning algorithm, which finds the structure of the agents so that we can determine to which node I should send the exchange the messages for distributed inference. And as the performance of our proposed inference structural learning algorithm, we analyze the sample complexity, which means that how many samples we need to have the consistent, the cost-efficient data graph from our structural learning algorithm. Okay, so let me first explain the model and backgrounds here. So we first modeled the underlying statistical uncertainty of the data samples as undirected graph. Here, the node is associated with the random variable of each agent. For example, this value corresponds to the data generated by each agent. And here, the edge structure captures the statistical dependency among these random variables, which means that non-adjacent random variables are conditionally independent given all other random variables. Here, we focus on the tree structure data graph, which has this factorized joint distribution form with each node potential functions and each edge potential functions. And here we also consider the case that we have n data samples from the unknown joint distribution, which is the tree structure distribution, and we now study how to learn the cost-efficient data graph using this observed finite number of data samples.
What is a tree? It is an assumption that it is a tree?
Yeah, tree. And the inference task of our interest is a focus on the maximum a posteriori, which I explained previous, which is to find the configuration with the maximum joint probability. And it is well known that there is a well-known inference algorithm, distributed inference algorithm. It is a max product, which is based on the message passing between the nodes. And given the data graph model, like this structure, Each node exchanges the messages with neighbors. So here, each node exchanges messages mi to j at each iterations. The messages is consisting of this potential factorized term, and the messages are iteratively updated. At each node I, they receive the messages from the neighboring nodes, and they update the messages like according to on this form, and they send the message to the another neighboring nodes. These iterations can converge to the exact solution of the map inference task if we consider the tree structured graph. And here, to analyze the various impact of the different communication cost from the inference, we consider two distributed map methods, which has some different message passing scheduling protocols. First is the synchronous algorithms, which send the messages are passed from the leaves to root and downward to the leaves again. Following this protocol, only two messages on every edge is required in the case of the tree structured graph, and so that we have the total amount of cost like this. Here, Cij is from the given physical connection of the agents, which is determined by the given physical communication connection. Another one is known as a parallel message passing algorithm, which is we call the synchronous. Here we repeat the message passing at every iteration, and so we don't consider the scheduling protocol. And in this case, we need at most diameter of the tree iterations to obtain the exact solution of the map solution. Because the diameter of the tree is the time that two most distant nodes should be reached, so that in this case we have a lot of more amount of the total communication cost, which is multiplied by the diameter of the tree. So now I introduce the three kinds of our main results here. The first is how to characterize and how to study the optimal cost-efficient data graph, which captures the trade-off between the inference accuracy and the communication cost from the two different inference methods. To this end, we formulate this kind of optimization problem, which is from given n data samples from the unknown joint distribution, we want to find the tree structure Q, which has this kind of objective functions. Here we consider two kinds of metric here. One is the inference quality, which is represented as KL divergence between the underlying data dependency from the n number of data samples and the Q tree distribution. And the second one is the communication cost, which determines on the distributed inference methods. We here again tested the two kinds of different distributed methods. In the case of the gamma is a trade-off parameter, and in the case of the zero parameter value, it's just the structural learning problem, which is well known in the machine learning. So here I want to explain some example of the cost-efficient data graph structures. For this asynchronous inference methods, as we focus on the communication cost, the resulting cost-efficient data graph follows the physical graph, while in this case, the resulting optimal solutions tries to have the smaller diameter. For example, in this star topology. The next result is about the structural learning algorithm for different two distributed inference methods. Here, for asynchronous, at the first step we compute the empirical mutual information from the n samples, which can be done by counting the number of the values, and we set the edge weight for every node pair as this amount, and we just find the maximum weight spanning tree as a result. Here we have that this algorithm considers the optimal tree solution of this optimization problem, because for the tree distributions, the minimization of the KL divergence can be equivalent to find the maximization of the sum of the mutual informations. So in this case, instead of this the data graph with the 3 and 6 edge, we choose the 5 and 6 as an edge because it has less communication cost. And second, in the synchronous case, we show that obtaining the optimal solution for this problem is NP-hard with respect to the number of nodes, because this objective function contains the diameter, which should be different for every possible tree distribution cube. So we propose a greedy heuristic algorithms, which the edge weight is the change of the objective values by adding the one edge E to the existing the tree structure. But we here consider more the additional term, which compensates the change of the edge weight in the previous tree structure and the new tree structure by adding the new edge. And we also add some constraint compensation term to keep the expected diameter growth of the resulting structure as the root of the number of nodes. Here, from this example, we can see that by choosing this, recovering these edges, we recover this edges as a result, which reduce the diameter of the resulting tree from the 4 to 3, which can reduce the communication cost internally. So this is the simulation results from the 20 node size graph. Here we see that as the gamma with the 0, these two kinds of structural learning algorithm consider the exact data graph, while as we increase the value of the trade-off parameters, it focuses on to find the cost-efficient data graph, which has a minimum communication cost for both kinds of distributed inference methods. Here, because the communication cost is constructed like this structural learning algorithm recovers the physical graph as a result. But in the synchronous case, because we also should to reduce the diameter of the resulting tree to have the minimum communication cost, it finds the star topology as a result. And this is the trade-off for the various trade-off parameter as the inference quality and the communication cost. The final result is about how many samples is required to have the consistent cost-efficient data graph, which means that what is the error rate of our two learning algorithms, and we analyze this by the large deviation principle. So we characterize the exponential decay of the error rate, which is that the learned graph structure from the n number of samples are not equal to the sufficiently large number of samples. And we characterize this exponential error rate by using the large deviation principle. Basically, to apply the large deviation principle, we consider a single candidate of the error events of our algorithm as a crossover of the edge weights from the true edge weights from the sufficiently large number of samples. So following the large deviation principle, we can characterize the error rate as the most probable crossover events, which means that pick a wrong edge instead of the most probable replacement edge. Which means that if we have the infinite number of data samples, we should find the edge 3, 4 instead of the 2, 4. But if we have insufficient data samples, we might have choose the edge 2 and 4 instead of 3, 4 from the imperfect information from the data samples. As a result, we have this analytical finding about the upper bound of the error probability with respect to the number of data samples, which means that the error probability is upper bounded with this term and with respect to the size of the samples. And this error rate can be characterized depending on the true mutual informations of the each node pairs and trade-off parameter value gamma. And also, as you remember, this edge weight is determined by the physical topology. It depends on this physical topology structure. We also have two simulation results about the third results. For the synchronous and synchronous distributed methods, as the sample size, we see that the error probability of our graph structure learning algorithms decay exponentially. And also, for the different value of the trade-off parameter, we have a different this shape of the error probability. But here we can find that for the large value of the gamma, which means that we put more priority to the communication cost instead of the inference quality, so that our problem is to find the data dependency graph with the minimum communication cost. So that in that case, since the communication cost is deterministically given, there is a less chance of the error events. In summary, in this paper, we studied the structural learning of the cost-efficient data dependency by considering the two different distributed map methods. And we see the trade-off between the inference quality and inference cost for both cases. And we also propose two different structural learning algorithms and characterize the exponential decay of the error rate. And as a future work, we can think about because we focus on tree graph structure and the map inference task, we can extend this results to more general data graph and general distributed